Welcome to The Explainer. Okay, let's dive into this, because today we are unpacking one of the absolute most mind-bending mysteries in modern astrophysics. We are talking about cosmic recycling. You see, for the longest time, we thought of black holes as these final, silent endpoints of massive stars, just dead ends in space. But it turns out the universe is way more chaotic and, honestly, a lot more creative than that. We are actually finding evidence right now that black holes act kind of like cosmic Russian nesting dolls. They merge, they grow, and then they literally merge again. It's an incredibly violent, completely invisible process that we're only just beginning to uncover, and the implications for how we understand the evolution of the cosmos are absolutely massive.
So I want to pose this question directly to you. What actually happens when a black hole swallows another black hole? It sounds like some wild hypothetical thought experiment, right? But this is the exact detective story we are unraveling today. When two of these absolute gravitational titans collide, they don't just vanish into nothing. They create something brand new, something much heavier, and crucially, something that carries the scars, the actual gravitational fingerprints of that epic collision. We're going to look at the exact signals that finally gave us the smoking gun for this whole process.
To really get this, we need to define our main suspect. A second-generation black hole is exactly what it sounds like. It's a black hole that formed not from the traditional route of a dying, collapsing star, but from the merger of two previously existing black holes. Now, scientists have been predicting the existence of these cosmic nesting dolls for years, but, predicting them on paper and actually proving they're out there are two very different things. But now, thanks to some mind-blowing new data, we finally have our very first direct proof.
Which brings us to Section 1, Catching Spacetime Ripples.
To find these invisible collisions, we have to completely change how we look at the universe. We have to transition from looking with light to literally feeling it with gravity. We detect these massive collisions by catching the spacetime ripples they generate, which we call gravitational waves. We do this using the huge LIGO, Virgo, and Kagra observatories. Together, we call them the LVK network. These are giant, L-shaped laser interferometers, and they are so incredibly sensitive they can measure a distortion in spacetime smaller than a fraction of a proton. And let me tell you, this network has been incredibly busy lately. The recently released GWTC5 catalog, that stands for Gravitational Wave Transient Catalog 5, just added a staggering 161 new, validated gravitational wave events to our records. These were all captured during the latest observing run, a period scientists call O4b, just between April 2024 and January 2025. In less than a year, they caught 161 distinct ripples from deep space. It's a massive leap forward, showing just how ridiculously far this technology has come.
To put that into perspective, this latest batch brings the total number of confirmed gravitational wave events since that very first groundbreaking detection back in 2015 to an astounding 390. Think about that. We have officially moved way past the era of just trying to prove the gravitational waves even exist. We ushered in an incredible new era of precision statistical astronomy. With 390 events, we don't have to just look at individual weird anomalies anymore. We can actually start looking at entire populations, at overarching trends, and we can start mapping out the hidden demographics of black holes across the entire universe.
Now, what's really interesting about this slide is the stark difference between these two origins. How do we actually tell these populations apart? Like, how do you know a black hole is second generation just by listening to it? Well, it all comes down to two things: mass and spin. A standard first-generation black hole that formed from a dying star generally has a pretty standard spin, and its mass is dictated by the original star it came from. But a second-generation black hole, that's the product of a violent cosmic blender. The orbital momentum of the two parent black holes gets directly transferred into the spin of the new one, so it's spinning incredibly fast. And, super interestingly, they seem to clump together in a very distinct mass range of about 10 to 20 solar masses.
Let's move on to Section 2. Meet the second generation.
This brings us to the absolute stars of today's explainer. Out of that massive GWTC5 data drop we just talked about, scientists flagged two highly anomalous signals. These were definitely not your run-of-the-mill stellar collapses. Let's look at their rap sheet. The events are named GW241011 and GW241110. They were detected just a month apart, in October and November of 2024. One of them happened about 700 million light-years away, and the other a staggering 2.4 billion light-years from Earth. When astronomers dug into the data, they saw the undeniable fingerprints we just mentioned. They had masses right in that sweet spot of 10 to 20 solar masses, paired with exceptionally rapid spin signatures. These black holes were just spinning way too fast to have been born from a single dying star. They absolutely had to have been built from a previous collision.
All right, section 3. Inside dense stellar clusters.
But where in the universe could this repeated, chaotic recycling possibly be happening? Because space is, mostly empty, right? For two black holes to just find each other is incredibly rare. For a newly merged black hole to then find a third black hole to merge with, you need a very specific, incredibly crowded environment for that. As astrophysicist Carl Johann Haster from UNLV pointed out, binaries like these had been predicted given earlier observations, but this is the first direct evidence for their existence. It's one thing to run a cool computer simulation showing that black holes could merge repeatedly, but seeing the actual ripples in spacetime from GW 241011 and GW 241110, that confirms that our models of these extreme cosmic environments are actually spot on.
So, the crucial point is figuring out the why. Mario Spera from the Virgo collaboration puts it perfectly. He notes, the puzzle is not simply that these black holes spin fast, but why this subpopulation appears precisely at these masses. That right there is a huge hint that the universe is hiding something fundamental about how these objects evolve. The leading theory right now is that they form in incredibly dense, crowded stellar clusters. In these tightly packed cosmic neighborhoods, gravity sort of acts like a sieve, much like heavy stones sinking to the bottom of a riverbed. The heaviest objects, which are the black holes, sink to the very center of the cluster in a process called mass segregation.
Let's walk through this whole cosmic recycling process step by step. First, massive stars in the cluster live fast, die young, and collapse into standard first-generation black holes. Second, gravitational interactions cause all these black holes to sink toward that densely packed center of the cluster. Third, and here is where it gets really chaotic, in this crowded mosh pit, they inevitably pair up and merge, creating a much heavier, rapidly spinning second-generation black hole. And finally, because it's still trapped in that super dense center, this brand new second-generation black hole finds another partner, merges again, and sends the space-time ripples from that collision out across the universe, eventually washing right over our detectors here on Earth.
And that leads us to Section 4, the Cosmic Symphony.
GW 241011 and GW 241110 are really just individual notes in a much, much larger composition. When we look at the full spectrum of gravitational waves, and this brilliantly illustrates the sheer scale of what we're tuning into, it's just mind-blowing. On one side, we have high-frequency waves operating between 10 and 1,000 Hertz. These are the quick, high-pitched crashes detected by the LVK network, produced by the final violent fractions of a second, when stellar mass black holes finally merge. But on the totally opposite side, we have low-frequency waves in the nanohertz range. These are detected by global collaborations like Nanograv using things called pulsar timing arrays. These waves take years, sometimes even decades, just to complete a single oscillation. They represent this deep, persistent background hum of the universe. This hum is produced by pairs of supermassive black holes. We're talking monsters millions or billions of times the mass of our Sun, slowly waltzing together in the centers of merging galaxies. Their orbital dance vibrates spacetime over millions of years, exactly analogous to the way heavy, waltzing dancers rhythmically vibrate a wooden dance floor.
Now, why does all this matter? Well, for all of human history, we have only ever been able to look at the universe using light. But black holes, by definition, emit no light. Now, with every single new catalog release, with every 161 new events we find, we aren't just looking at math on a page anymore. We are literally hearing the invisible violent evolution of the universe in real time. We are charting populations of objects that were completely hidden from us just a decade ago. We're literally watching the universe recycle its most extreme objects.
Which leaves us with a truly fascinating question to ponder. If these dense stellar clusters act as cosmic manufacturing plants, churning out these rapidly spinning second-generation black holes that sink right back into the fray, what will a third-generation black hole look like? Will its intense spin literally tear it apart? Or will it grow into a massive, intermediate mass black hole? As our detectors get more and more sensitive every year, honestly, it's only a matter of time before we hear the answer to that question ringing across the cosmos.